Welcome everybody. So welcome to our new semester. So by God's grace, you all have cleared your fourth semester examinations successfully. So, okay. Hope you are all doing good. And this semester, I'm going to take structural analysis 2 for you. So our course code for structural analysis 2 is CE303. So course is structural analysis 2. So for studying structural analysis 2, you need to have some knowledge about what you have studied in structural analysis 1 and mechanics of solids. A small revision on mechanics of solids. So mechanics of solids, you study about rigid bodies. And you have studied how to draw, how to analyze the shear force and bending moment for beams. Okay, so you know how to analyze simple beams, how to draw, if you know the reactions and the loading conditions, how to draw the shear force and bending moment diagrams. So without knowing this, you cannot proceed. Then in the structural analysis 1, we saw how to analyze a truss. We studied unit load method and method of consistent deformation to analyze, to find the deflection of indeterminate beams. Now, then we saw influence line diagrams. We know how to draw the influence line diagrams for simply supported beams, for beams with overhangs, etc. Then we saw about arches, cables and suspension bridges. So these things we studied in our structural analysis 1. Now in structural analysis 2, this is the continuation of structural analysis 1. So here we are going to analyze some complicated structures. That is, here you will be analyzing indeterminate beams. So first 4 modules will be about indeterminate beams and frames. And the last module will be, first 3 modules are about analyzing the indeterminate beams. 4th module is about analyzing of curved beams. And last module is plastic analysis. So, today we will start with our first module. You all know me well? Okay. So our first module is about 3-moment equation. Okay, it is 3-moment equation. Now, this 3-moment equation is nothing but, see, already you have studied unit load method and method of consistent deformation to analyze the beams and frames. Now, this is another method to analyze indeterminate beams. And this beams is mainly used, this concept is mainly used for analyzing the continuous beams. Okay. So when a beam has more than 2 supports, you will call it as continuous beams. So for a continuous beam, you can have simple supports at the ends or fixed support at the ends. Sometimes you may have overhang also. So this theorem was introduced by Clapeyron. So you call it as Clapeyron's theorem of 3 moments, or equation of 3 moments, or theorem of 3 moments, or 3-moment equation. So you have to study. So basically first module is about Clapeyron's theorem. If you know this theorem well, if you know how to apply this theorem, you can easily solve the problems of the first module. Now you need to study about the derivations of 3-moment equation and the application, how to use this 3-moment equation for analyzing our beams. Now, before going inside the syllabus, that is before discussing about Clapeyron's theorem, you need to know what is a continuous beam, what is an indeterminacy of the continuous beam, how to determine the indeterminacy of continuous beams. What is the difference between the bending moment of a simply supported beam and a continuous beam or fixed beam? So these things we are going to study in today's class, and we will start the Clapeyron's theorem from the next class. So today you are going to see what is a simply supported beam, what is a continuous beam, what is the fixed beam, how to find the indeterminacy of a beam, statical indeterminacy of a beam, and the comparison of bending moments. Let us see what is a statically determinate beam and an indeterminate beam. So first of all, a statically determinate beam. Normally, a simple beam is the one which is supported by a hinge on one end and a roller at the other end. So such beam can be called as a simply supported beam. Now, for such a beam, the reactions are determined by using the static equilibrium equations. We know the static equilibrium equations are sigma h is equal to 0, sigma v is equal to 0, and sigma m is equal to 0. So by using these three static equilibrium equations, we will be able to determine the reactions. For example, in this beam, the reactions, if we take these support as A and as B, the reactions can be taken as RA and RB. So, by using the condition sigma V is equal to 0 and sigma M equal to 0, and if there is any loading conditions, we will be able to determine the reactions RA and RB. That is why we call this as a statically determinate beam. Now, if the ends of the beam are restrained or clamped or encasted or fixed, so that means there will not be any simple supports, it will be fixed at one end or fixed at both the ends. So in such case, when the supports are fixed, there will be a restraining moments which will make the structural element to be a statically indeterminate structure or a redundant structure. The reason is, when the loads acts on the structures, on such a beam, if you are taking this support as A and the right support as B, the reactions acting at A will be a vertical reaction, a horizontal reaction, and there will be a moment. Same way at B, there will be a vertical reaction, a horizontal reaction, and there will be a moment. So, totally we have 6 reactions, 6 unknowns, and only 3 equilibrium equations are available. Therefore, the statical indeterminacy becomes 3. We need additional 3 equations to determine the unknowns. That is why such a beam becomes statically indeterminate beam. Now, so because of these restraints means these restraint, because there will be moments. Okay, so since there are restraints, these restraints will make the slopes at the ends 0. So since there are restraint, when you are taking the deflection, the slopes will be equal to 0, S will be equal to 0, whereas when you take a simply supported beam, your deflection will be like this. So the slope is not equal to 0. Slope not equal to 0. Here at the support, the slope will be equal to 0. So the slopes at the ends becomes 0, and hence in a fixed beam, the deflection and slopes are 0 at the support. So when you consider a fixed beam, your slope is equal to 0, your deflection will also be equal to 0 at the support. Now, let us see what is a continuous beam. So, how can you describe a continuous beam? The general conditions describing the continuous beam are: number 1, the beam should have more than one span. That is, when it is one span, you call it as a simple supported beam. And when they are fixed at the ends, you will call it as fixed beam. But when it has more than one span, we call it as a continuous beam. Now the second condition is it should have more than two supports. Number 1, 2, 3. So you should have at least 3 supports to define a continuous beam. And these beams are statically indeterminate. That means the number of reactions are more than 2 or 3. 2 when we are omitting the horizontal reactions. Here we know our equations of equilibrium are sigma h is equal to 0, sigma v is equal to 0 and sigma m is equal to 0. And when we have only vertical loads, we omit this condition and we take only these two conditions. That is why it is written as more than 2. So in actual it is more than 2 or more than 3. So statically indeterminate, that is the number of reactions are more than 2 and only 2 equations are available from structural equilibrium for vertical system of loading. Okay, so see, you can take this example. We have one reaction at this support, another reaction at this support and the third reaction at this support. So we have 3 reactions and we have only 2 equilibrium conditions for the vertical system of loadings. That means for this beam, the statical indeterminacy becomes 1. Therefore, the continuous beam is always a statically indeterminate structure. Now, let us see how to determine the statical indeterminacy of a continuous beam. So we will see this with the help of examples. We are taking vertical system of loadings. So consider a beam. Now the beam are supported by 3 simple supports. 3 simple supports. Now there 2 vertical loads are given in the supports. Therefore the statical indeterminacy is 3 minus 2. 3 is the number of reactions. We have, if you are taking the support as A, the right support as B and the center support as C, we have the reactions RA, RB and RC. Therefore, our R is equal to 3, unknown reactions is equal to 3. Our equations of equilibrium are 2, that is sigma V is equal to 0 and sigma M is equal to 0. That is, summation of all the vertical loads is equal to 0 and the summation of moments is equal to 0. So our statical indeterminacy is 3 minus 2. So we get 1. We will go for another example. So you have a beam. It is supported by a fixed support at A simple support or a hinged support at B and a simple support at C. It is loaded by 2 vertical loads. So our statical indeterminacy becomes 4 minus 2. That is, at this point, at this support A, we have a vertical reaction. We will have a vertical reaction RA. You will have a moment MA. So number of reaction is 2. Here at the simple support you will have reaction RB and at C you have the reaction RC. So 2, here RB is 3 and RC is 4.
So totally it is 4 minus 2. 2 is the number of equilibrium equations available to solve your problem. Now the third example is, it is fixed support at A, another fixed support at B, and a simple support at C, loaded by two vertical concentrated loads. So our number of unknowns R is equal to 5. How R is equal to 5? See, here you have RA, we have a moment MA. So two reactions here, two unknowns at A. RC, so one unknown at C, and we will have vertical reaction at B, that is RB, and a moment at B. So it may be clockwise or anti-clockwise. So totally we have 5 unknowns. So it is 5, and the number of equilibrium equations available is 2. So it is 5 minus 2, it is 3. We will see one more example. So it is fixed at A, fixed at B, and you have a hinge at C. So when a hinge is introduced in your beam, your equilibrium equation becomes +1. That is, here your statical indeterminacy becomes R minus N, where N is the number of hinges. So here R is equal to, you have two reactions here, two reactions here. So R is 4 minus small r is 2, that is number of equilibrium equations is 2, minus N is 1. N is the number of hinges. So you have one hinge, so it is 1. So you get, you have two more loads, two more supports. So here you have one unknown. At this support you will have one unknown. So total unknowns is 6. So you will get the statical indeterminacy as 6 minus 2 minus 1, it is equal to 3. Now let us see the comparison of bending moments for a simply supported beam and a continuous beam. So for that we will take a simply supported beam first. For simply supported beam, when it is subjected to a single concentrated load of W, we know the bending moment diagram for such a beam is W L by 4 at the center, and it will be 0 at the supports. At the supports there will be 0 bending moment because of simple supports. And if the ends are fixed, and it is subjected to a single concentrated load W and the span length is L, the bending moment diagram becomes a triangle. So it is, the magnitude is WL by 4 at the center of the beam, 0 at the supports due to the simple bending, and there will be a bending moment due to this fixed supports at the ends. So that bending moment will be drawn like this. So you can see that this is this triangular portion. In the first case, this bending moment is positive, whereas in the second case, the bending moment is positive as well as negative. So positive at the center and it is negative at the supports. So at the supports, due to the fixed or due to the restraints, we will have negative bending moments. Now we will extend this for continuous beams. So before extending for continuous beams, we will see one more example with UDL. So when a simply supported beam is subjected to UDL of W per unit length, the bending moment diagram will be drawn as a curved parabola. It will be like this. So the maximum bending moment will be at center and it is equal to WL square by 8. And the bending moment at the supports will be equal to 0. Now, when we are extending the bending moments for the fixed beam, when the supports are fixed and when the beam is subjected to an UDL of WO per unit length, our bending moment diagram becomes a parabolic due to simple bending, it is WL square by 8, and we will have a fixed bending moments at the supports. So this is positive and here we have this part is positive and this part is negative. So we will have negative bending moment at the supports and positive bending moment at the middle of the beam. So this concept we are going to extend for continuous beam. Now, when we are considering a continuous beam, suppose we have three spans with simple supports. Imagine we have three spans with simple supports. So we have concentrated load at first support, we have an UDL at the second span, and again a concentrated load at the third span. So our bending moment becomes like this. Our bending moment diagram will be drawn like this for simply supported beams. Now, when it is extended with a continuous beam, so since it is three spans, we will have four supports, 1, 2, 3 and 4. So we have four supports. So in these four supports we will take the same conditions of loading, concentrated load, UDL and again a concentrated load. So how will we draw the bending moment diagram? It is the bending moment due to simple supports is like this, and due to fixed support, that is, see here the end supports are simple supports. If the end supports are simple supports, you will have zero moment at the end support. But the intermediate supports, even though the intermediate supports are simple supports, it will have some negative bending moment, restrained effect because of this intermediate supports, so that you will have some moments at this part. So that moment will be a negative moment. So when you are drawing the bending moment diagram, you will have a positive bending moment and negative bending moment. You will have negative bending moment at the intermediate supports and positive bending moment at the other places. So in the intermediate supports we can choose another color, so that we will choose the blue color. So here we will have negative bending moment. So this is negative and this is positive, positive, positive and positive. Now suppose here it is, we will make it another color. Okay, suppose the end supports are fixed. In the second case, suppose the end supports are fixed, our bending moment diagram will be changed to, the fixed bending moment diagram will be changed like this. You will have some bending moment, negative bending moment at the support also, if these simple supports are replaced by fixed support. Now, so what do we infer from this? The reactions of individual beams can be obtained by equilibrium equations alone. That is, for these cases, see, for each individual beam, only two unknowns for the first beam, again two unknowns for the second beam, two unknowns for the third beam. So you can determine the reaction of individual beams by using the equilibrium equations alone. But what is the case for the continuous beam? There is number of unknowns are 1, 2, 3 and 4. Suppose if it is fixed, you will have 2, at the fixed support, one at the simple support, another one at the simple support, and 2 at the fixed support. So totally you will have 6 reactions. Now the equilibriums, therefore you have only 2 equilibrium conditions, but we have 6 unknowns. So the equilibrium equations alone would not be sufficient to determine the end moments. Now the beam deflects in the respective span and does not depend on the influence of the adjacent spans. It depends on the individual spans. Okay, the bending moment depends on the individual spans. Whereas in the case of continuous beam, the equilibrium equation alone is not sufficient for determining the end moments. Also, the magnitude of the slope can be influenced by not only by the load on the spans, either side of it, but the entire loads on the span of the continuous beam. So, the slopes, see here, if it is fixed, the slope will be equal to 0. But if it is simple support, the slope is not equal to 0, and in that case, the slopes and deflections and bending moments are influenced by the entire spans, the entire loading systems. So, this is the difference between, or the comparison between, the bending moments for a simple supported beam and for a continuous beam.